In this section, we're going to be discussing polynomial functions and looking at some different characteristics they have, but also looking at their graphs and actually doing the graphs of polynomial functions. Okay. What I have here would be like just a general format of what a polynomial function looks like. All this is, if you'll notice, like here I have x to the n, here is x to the n minus 1, so like this one is 1 less than this one. This is just indicating the descending order, like you just, go down a power each time. Of course, I've got the dot, dot, dot in the middle because how many terms you have in your polynomial are going to vary from problem to problem. But it works its way down, finally to second power, first power, and this would represent your constant. Now the a sub n minus 1, the a's are just representing the coefficient of each one of those terms. The subscripts, they just have to do that to name them in different ways. So this one's called a sub 2 because it belongs to x to the second power. This one's a sub 1 because it belongs to a to the first power, and so on. When you have a polynomial function, you would refer to it as having a degree of n. So n, back up here, see, is going, if this is in descending order, this is going to be your largest exponent. So the degree of the polynomial is always your largest exponent. A sub n, which is the coefficient of the variable to the highest power, is called your leading coefficient. So if this is my x that's to the largest power, its coefficient is referred to as a sub n. It is a coefficient, but that one specifically is called your leading coefficient. Now the n, of course, which is what they're using as the exponent, that's the letter they've chosen, refers to it as being any non-negative integer. Now a non-negative integer is basically your whole numbers. Like that would have to be 0, 1, 2, 3, and so on. So that would be, like I said, non-negative integers. Okay, next. Here we're asked to determine which of these are polynomial functions and what is the degree of each. So there's a couple of things that you look for to let you know for sure that it's not a polynomial. This first one is a polynomial as long as, one thing to pay attention to is that your exponents, of course this one's an understood one, your exponents need to be non-negative, as we just finished talking about. But another thing is, like, x's are not going to be in your denominator. You're not going to have fractions as exponents. Okay, so these need to be positive. They need to be whole numbers. Doesn't matter about the coefficient. The coefficients can be any real number. So you would say that yes, this is a polynomial function. And as I showed you just a few minutes ago on that previous slide, the degree is referred to as n, but n is just your largest exponent. So in this case, my degree is 7. Okay, on the next one, this one is not a polynomial, and it's this term right here that keeps it from being a polynomial, because if you were to rewrite this, this is the same thing as 2x to the negative 1. And as we talked about, your exponents have to be integers that are non-negative. So just the fact of having the variable on the bottom, that's another way of looking at it. Dead giveaway, it's not a polynomial. So if it's not a polynomial, it's not going to have a degree. All right, the next one, the problem with number 3 is that being to the 1/3 power. Again, going back to the fact that your exponents have to be non-negative integers. 1/3 is not an integer, so this is no. Now, this one is yes, even though it doesn't look like what you're used to seeing, because I could actually rewrite this. Like if you split it up, I could have 1/3. Of course, the 1's understood to be there. 1/3 x squared plus 7/3. Okay, so this is just my constant. You can see right here, my exponent is a non-negative value. So this is yes, it is a polynomial, and its degree would be 2. Okay, here's a little description of polynomial functions that you'll need to write down. But polynomial functions of degree 2 or higher. So this does not include polynomials to the first power, because polynomials to the first power are actually just lines. So a second degree or higher, the graphs are smooth and continuous. So what it means by smooth is what I refer to as having like hills and valleys. You know, smooth rounded curves. You can't have any sharp corners in your graphs. What it means by continuous is that you can trace it from the left side to the right side without ever having to pick up your pencil. There's no interruption in your graph, like for instance a vertical asymptote or even just a hole in the graph. So continuous is one continuous motion with the graph without any interruption. Okay, so using that concept, which graphs would have to be polynomial functions? Alright, so the first one, so this is what I would refer to as a hill and a valley. So you've got nice, smooth, rounded curves, but it is also continuous, because if I trace this from one side to the other, I don't have to pick my pencil up at all. So this one would be the graph of a polynomial. Number 2, this one would not be because of the sharp turn right here. See, that's not smooth and rounded. That's that sharp turn that I referenced a while ago. Okay, this one would be a polynomial. Get nice, smooth, rounded curve. But again, if I trace it from one end to the other, there's no interruption in that graph. Now, number 4 is not going to be one. Now, it would be considered smooth. There's not any like sharp turns, sharp corners. But this one's not continuous, because if I trace it, once I get to this spot, I have to pick my pencil up, then put it back down and continue tracing it. So this one's not continuous. So only number 1 and number 2 would be graphs of polynomial functions.